In the last video, we wrote code to implement the depth-first search algorithm, which is an online uninformed search method. And we used our code to do some experiments with adding memory to the algorithm, adding an element of randomness, and adding and removing barriers. Now we'll look at two other algorithms, breadth first, an offline uninformed search, and AStar, an informed search that can be run either as an online or an offline search. The breadth first search algorithm works like this. We start by investigating every possible action from our start state, and we check to see whether the resulting state is the goal, a barrier, or neither. If the state is neither the goal or a barrier, we label the state with the number 1, representing the number of actions that were required to get there. If the state is a barrier, we do not label it. If the state is the goal state, we stop searching and then move backwards to the start state. So suppose that we investigate every possible action from the start, and none of the resulting states is the goal. We label all of these states with a 1, but we do not label any of the barrier states. Next, we start at each of the states labeled with a 1. We investigate each possible action from these states. If the resulting state is a barrier, it is not labeled. But if it is neither a goal nor a barrier, we now label it with a 2, because we have taken 2 actions to get there. Then we start at each state labeled 2 and investigate each possible action. Any resulting state that is neither the goal nor a barrier gets labeled 3, and barriers do not get labeled. Now we start at each state labeled 3 and investigate each possible action. Suppose that here we find the goal state. From the goal state, we step backwards from the goal state, which is number 4, back to a state labeled 3, then backwards to a state labeled 2, then backwards to a state labeled 1, then finally back to the start state. We keep each of these actions in a list as we're moving backwards. Finally, we have the robot execute this list of actions in the correct order. The breadth first algorithm has a lot of advantages over the depth first algorithm. First, the breadth first algorithm will always find the shortest path possible from the start state to the goal state. Also, the robot will never get stuck in a loop as it does with the depth first algorithm, because the breadth first algorithm is always considering all possible moves. But the breadth first algorithm has some drawbacks too. Probably the most important drawback is that this method is super computationally and memory intensive. For example, suppose that we always have 4 possible actions that the robot can take. By only the 10th step, we already have more than 1 million possibilities to investigate for state number 11. If the problem to be solved is even moderately complex, the resources required to solve the problem quickly become extreme. Also, since the robot can't physically jump from branch to branch like this, the robot can't take any actions until it has completed all of its thinking. If the robot's environment is somewhat dynamic, its solution might not even be valid anymore by the time it has found it. So let's take a look at one more algorithm called AStar. AStar is different than depth first and breadth first in that it is an informed method. In order to use AStar, the robot has to have a way to at least estimate the distance from its current state to the goal state. But if you do have this capability, AStar will generally work better than either depth first or breadth first algorithms. Here's how AStar works. Every potential action that the robot can take is given a score. The score is equal to the sum of the cost of taking the action plus the distance that the robot would be from its goal state if it took that action. The robot calculates the score of each potential action, then takes the action with the lowest score. For example, suppose that in our navigation problem we assign a cost of 1 to the action of driving into an open square. And suppose we assign a cost of 1,000 to the action of driving into a barrier. The 1,000 cost is really high because driving into a barrier is really bad. The robot will break. Driving into an empty square isn't really bad, but it does take some time and energy, so we do give it some cost, although the cost is low. So suppose the robot is positioned here, and there is a barrier at an angle between the robot and the goal, like this. The robot will consider each possible move. The cost of driving into the barrier is 1,000 plus the distance between this point and the goal. The cost of driving away from the barrier is 1 plus the distance between the goal and this point, which is farther away. The cost of driving along the barrier this way is 1 plus this distance, and the cost of driving along the barrier this other way is 1 plus this distance. The robot won't drive into the barrier because its cost is the highest. Then, among the other 3 possibilities, the robot will drive in the direction that most minimizes its distance from the goal, because the cost of each of these 3 actions is the same. Now, AStar isn't a perfect algorithm either. Without some additions like memory or some rules to allow it to explore alternate routes, AStar can still get stuck in loops. This is especially true if the method that you're using to estimate the distance between the robot and its goal is not a perfect measure. However, AStar also has a property known as being complete. A complete search is one that will always find a solution as long as one exists. The breadth-first search also has the property of being complete, but AStar in general will be less computationally intensive than the breadth-first search. So how do you choose which type of search method to use for a given problem? In general, informed methods will perform better than uninformed methods. And then, to choose between online and offline methods, you have to weigh considerations of computational intensivity and also issues like time. If you can wait for the robot to think through the entire problem before making a decision, then an offline method will probably work better than an online method. But in all cases, choosing and designing a good search algorithm takes a certain amount of trial and error and testing the robot in the environment that you intend it to work in.